And today we are looking at section 5.5, the mean value theorem and Rolle's theorem. Our objective is to examine the mean value theorem and Rolle's theorem and to apply these theorems to solve problems. It's a pretty short lesson. I did want you to be aware, let me get my pen going here, that mean value theorem, a lot of times as we are writing it, we will do the little abbreviation MVT. That saves you writing it all the way out, just like on IVT for intermediate value theorem. Rolle's theorem, however, you have to write out. So let's get going. Look at these problems. We're going to do a few of them in class as we go through, so let me just do a couple of them and get you going, and then we'll work together tomorrow in class. Okay, I do want you to get this definition down. The mean value theorem states that if f of x is continuous on the closed interval AB and differentiable on the open interval AB, then there exists a number c between a and b such that f prime at c equals f at b minus f at a over b minus a. Now, a lot of times when people are looking at this, they look at this side right here and they think that that's just the definition of the derivative. But if you notice, that's missing the limit. This is actually saying this is the slope of a secant line over here. And so what you've got is that the slope of your tangent line, over here is going to be equal to the slope of the secant line. Okay, and I'm kind of out of room since I underlined that, but it equals the slope of your secant line. Okay, the slope of the tangent line equals the slope of the secant line. So look over at your picture, get the picture down. The fact that you have this visual image in your mind every time I say mean value theorem is really important. So you've got your function that's stretched out like this. Okay, here was your A, here was your B. It is continuous on the closed interval. It is differentiable on the open interval because remember, it cannot be differentiable at endpoints. There's not a slope of a tangent line. You can't take the derivative at an endpoint. So there's your continuous function, differentiable on the open interval. Then there has to be some number in between where the slope of this secant line is the same as the slope of the tangent line. And that value right there, coming right down through there, that occurs at an x value of c. Okay? So that guarantees that that's going to happen. All right, let's look at some examples. Okay, they say draw the secant line through two given points on the graph and then draw any tangent lines to the graph that are parallel and estimate the x value of the point of tangency. Well, we're going to look at a couple of these right here and then we'll look at two more tomorrow in class. This says I'm on the closed interval from 0 to 3. So I want to go from 0, 0, 3 ends up going through 3, so I'm going to draw a line that goes right in through there. Okay, now what I'm looking for then is another line just like that one, and let's duplicate or clone. Okay, it has to have the exact same slope, doesn't it? And I need to take that line and I want to move that to where it touches my graph and has that same point. Okay, well, I've got it just a little bit off, but if I move it just a little bit more, I think that's going to happen at right about 1.5. There it is. Okay, and so going back to my pen, that's where I get it at x equals 1.5. 1.5 is my c value where the mean value theorem is actually applying, where the slope of the secant line is the same as the slope of the tangent line. Okay, on the next one, I want to connect 2 and 4. So at 2, I am right here, and at 4, I'm going through the x-axis. So I've got a nice little line like that. Oh, slightly off. Okay. And I want to clone it. Okay, and that looks like that happens Although I've got it just a little bit off, it looks to me like that happens at x equals 3. Okay. So that's what we're looking at on these. That's what we're wanting to be able to do, is to draw those lines and get those secant lines parallel to our tangent lines. I'm going to let y'all look at these two right here. Somebody be prepared. I'm going to call you up to do those tomorrow in class. Okay, on these right here, it says draw the secant line through the 2 points corresponding to the endpoints, and then draw any tangent lines that are parallel. And what you're supposed to figure out is how many tangent lines there are. Okay, well, again, we're going to draw through. I'm going to get my line and draw through my endpoints like that. Well, that was pretty obvious. I mean, how many secant lines or tangent lines do I have that are parallel to that? Okay, I'm just going to have the one. It's just going to come over. Okay, and there it is, just one line. Okay. Then I move to this one over here. Now, the key thing that you want to notice on this one is that although I have this right here, the function is approaching that, my actual endpoint is down here. And so when I do my line, it's stretching from here to here. This function was continuous on an open interval, not on a closed interval. Okay, differentiable on the open interval, yes, but not continuous on the closed interval. And so since the endpoint didn't work, the number of tangents that I have on this one is 0. Okay, so you want to be really careful. It has to meet both requirements to guarantee that this happens. It might happen otherwise, but there is no guarantee that it will happen otherwise. Okay, so we're looking for it to be, again, continuous on the closed, differentiable on the open. Okay, we're going to have a couple more right here, and I'm going to let you look at those and figure out. Again, be ready to draw tomorrow. See what you can come up with. Show me how many tangent lines there are on each one of those. Okay, same thing on these right here. Figure it out. Okay, you're going to see on some of these that it happens even if it doesn't, even if those two things don't apply, but it's not guaranteed to happen unless it's both continuous and differentiable. All right, two more right there. All right, and then the last two right here. You can tell the one on the left, you're going to have to do a little bit of work to get that one to work from -3 to 3, counting how many tangent lines you have. All right. Now then, here's the problem I want to work out. Find the number c that's guaranteed by the mean value theorem for derivatives for g of x equals x plus 1 cubed on -1 to 1. This is where we actually get to see what we're doing. The other was a visual picture of it, but let's see what we're doing now mathematically. Okay, what has to happen on this is that g prime at c has to equal g at 1 minus g at -1 all over 1 minus -1. Okay, this is saying the slope of the secant line and the slope of the tangent line have got to be the same. Secant line's over here on the right-hand side, tangents on the left. Okay, now then the reason I can do this again, x plus 1 cubed, we know that that's a polynomial function. It's going to be continuous, not a big deal. It's going to be differentiable, so that's not a big deal. We're good to go. All right, so g prime at c, that's going to be 3 parentheses c plus 1 squared, right? Because that's my derivative evaluated at c. 3 times x plus 1 squared equals g at 1. When I plug 1 in right there, I get 2 cubed, which is 8, minus g at -1. -1 plus 1 is 0, so that's just going to be 0, no big deal. All over 1 minus -1 is going to be 2. So I end up right here with 3 times c plus 1 squared equals 4. Divide both sides by 3, and I have c plus 1 squared equals 4/3. To solve this, take your square root of both sides, right? Until you get c plus 1 equals plus or minus, don't forget that, 2 over square root of 3. And so then c is going to equal negative 1 plus or minus 2 over square root of 3. And I do not know, I've got 2 answers right here, but I don't know whether I have 2 actual points where this happens or not, because I have this really important interval right here, and I've got to make sure that my answers land in that interval. I don't know what 2 over square root of 3 is. I know square root of 3 is about 1.7, so 2 divided by 1.7, it's going to give me just a little bit over 1 here. Well, if I have negative 1 plus a little over 1, then that's going to be a little bit over 0, which should land in that interval. If I have negative 1 minus a little over 1, that's going to be negative 2 point something, which is not going to be in that interval. So my actual c value then here, where the secant line is parallel to the tangent line, is negative 1 plus 2 over square root of 3. Okay, and that's it. Right. And if you put this in your calculator, if you figured a tangent line with this at this point, then you'd be in good shape. The secant line would be parallel to that tangent line. All right. Rolle's theorem. Rolle's theorem is actually the mean value theorem, just expanded a little bit or done at different points. It's not just continuous on the closed interval and differentiable on the open interval. It is that, but the deal is that your 2 y values have to be the same. In other words, right here and right here, I have to be at exactly the same y value. And what this guarantees is that you have a slope of 0, okay? Or in other words, you're going to have a horizontal tangent line parallel to that secant line. Okay, so Rolle's theorem is the same as the mean value theorem, but it guarantees a horizontal tangent line, not just any tangent line parallel to your secant line. Okay? And we will work on this a little bit tomorrow and see what this means, but there's your basics. Again, if you need to go back and stop and get the formulas or anything like that down, be sure you've got those down. But I think that'll get us for tonight. Thank you. Bye.